Congratulations, you're moving on to outcome R4. That's quadratic equations in general form. So before we actually start diving in to manipulating that general form, the first thing that we need to do is understand what is a quadratic function and what are some main ideas behind it. So a quadratic function is any function that can be written in the form y equals ax squared plus bx plus c, where a and b are elements of the real, that means real numbers, and a cannot be 0. And like we discussed in the previous lesson, that is because if we take out our x squared term, now we're dealing with an coefficient times just x to a degree of 1 plus a constant, and that is our linear equation. So we have element of the real, so any real number, and a can't be 0. Oops. And otherwise we express it as y equals ax squared plus bx plus c. This is called our general form. So a function is any equation that can be described as having one y value for any x value. And so we can do the vertical line test to check. So that's why now we're calling it not only an equation, but we're calling it a function because it does pass this test. So start by just drawing the base or parent graph. So our base equation with no extra jazz to it is just y equals x squared. So we need to plug in some x values. We're going to figure out some y values. We want to figure out on both sides of our y-axis. So I'm going to start at -3 and might work my way over. -2, -1, 0, 1, 2, 3. If we plug this into the equation, we'll notice that y equals x squared. So it's going to take this x term and multiply it by itself. So -3 times 3 is, or -3 times -3 is 9. 4, 1, 0, 1, 4, 9. Great, now let's plot these. So I'm going to say that each tick is actually worth 1. So I'm going to make sure that I have that labeled on my graph. Always identify your scale. Okay. We should also name our axes, x and y, and you'll notice that these axes already have arrowheads on them, so we're set. Now we got to plot our points. Remember, it's x is horizontal, y is vertical. So we've got -3 and 9. So I go -3 and positive 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if I run into this kind of problem, I'm not going to use 1 as my scale on my y-axis. It's going to work great on my horizontal. I could have even skipped one and done like halves. Okay, but vertically I'm going to maybe have to go up by 2s and down by -2 to help myself out and fit it all in here. So -3, positive 2, 4, 6, 8, 9. 8, 9 is halfway. We've got -2 and 4, -1 and 1, 0 and 0, and I get a reflection of this on the other side. So we've got some symmetry here. Now this graph should maybe kind of look similar to what we saw in our activities at the beginning of this unit. We're going to connect these points with a curved line. Now, I apologize, it's not very smooth here. It's just my drawing on this surface. It's not quite up to snuff yet. And we're going to label our equation, or our graph, with the equation. So this is our parent function, our parent graph. And the shape that it makes is called a parabola. Every quadratic function is going to form a parabola. So this general shape we're going to be working with it a lot. So we're going to get pretty good at drawing parabolas. Make sure you practice saying it so you know how to say it right. Parabola, not parabola or anything along those lines. Okay, it's not some sort of illness. There's some key points that we need to label. So I'm going to kind of scroll back and forth. Maybe I'm going to zoom out a little bit so I can have it all on my screen. The first key point is the vertex. It is the highest or lowest point. If the graph opens upwards, it is the minimum, it is the bottom. If the graph opens downwards, it is the maximum. So on our graph, our vertex is at 0, 0. And it is a minimum because we're opening upwards like a cup. The second piece that we want to consider is our axis of symmetry. It is going to intersect the parabola at the vertex. That's its definition. And so the x-coordinate of the vertex corresponds to the equation of the axis of symmetry. So the axis of symmetry is literally if we took a mirror and put it down so that it cuts through our vertex at the x value, that is my axis of symmetry. And so in this particular case, it's always got an equation because it is a line. In this particular one, it is when my vertex is going through 0, so x equals 0. Always write an equation as your axis of symmetry. That's a big one. Some people just like to write the x value, but they forget the fact that it's an equation. The domain is all the possible x values. So is there any reason why I could not put a number in for x in this case? No. There's no dividing by zeros that I have to account for or anything along those lines. So my domain for all these regular parabolas is going to be infinity. So we've got two ways of writing that. I'm going to scroll down. Option 1 is to write it in interval notation. Option 2 is to write it in set notation. So I'm going to write it in both. I'm going to do this for domain and range. So for my domain, there's no restrictions. X could be absolutely anything. And we can see that on our graph because it keeps expanding wider and wider. Now it's going to get steeper and steeper, so that expansion to the left and the right is going to be really, really slow, but it is still happening. So I would say that it's from negative infinity to positive infinity. If we are going to do interval notation, we always write the minimum value followed by the maximum value. A round bracket implies that it is a value that doesn't actually exist, or it can't be reached. Alternately, a square bracket is a defined point. That's how we do interval notation. In set notation, I would say that x is my domain variable, and it is the x is an element of the reals. It could be any real number. All possible values, any fractions, repeating decimals, non-repeating decimals, all of those are all good to go. Our range, remember, so domain is your x values, range is your y values, and it really depends on where your vertex is. If we look back at our graph, and we imagine this graph is casting a shadow onto our y-axis. So there's a light source here, and it's shining this direction. Where do we get a shadow on our graph? Well, we get a shadow all through here, and it would keep going forever upwards. Because of that, and our shadow stopped at 0, we can conclude that our range also stops at 0 and can be anything above it. So it's got a minimum value, and that minimum value is defined, it's 0. our maximum is positive infinity because we could keep going up and up forever. Alternately, as our set notation, define our variable and say that y would be greater than or equal to 0. So anything above or including 0 is totally fair game. Anything below 0, even if it's negative 0.00001, no good. So those are our 4 key. In addition to that, we do see some old friends showing up again. We've got our x and y intercepts. So again, our x-intercept, if we don't remember, is where it crosses the x-axis, and our y-intercept is where it crosses the y-axis. In both these cases, we have the other variable, whether it be y or x, they are set to 0. Because we haven't moved left or right if we're talking about our y-intercept, we haven't moved up or down if we're talking about our x-intercept. We've stayed directly on the axis. So we'll start by completing our table of values. So we've got a little bit more complex equation this time. So I'm going to just write my work over here to see how it plugs in. In this case, y is going to be equal to, let's zoom in a little bit now that we've got that writing on the side. Y is equal to negative 4 squared plus 2 times negative 4 minus 3. Negative 4 squared is 16 plus 2 times negative 4 is negative 8, so that's going to be positive 8. Subtract another 3 is going to be positive 5. Now again, you don't have to do that all in your head. You can write down your steps, but I don't have a lot of room here, so I'm just going to write down the filled in forms and I'll do the mental math to make sure that this is working out. For negative 3, y equals negative 3 squared plus 2 times negative 3. Subtract 3 is my constant. Negative 3 squared is positive 9. We're going to subtract 6 is positive 3. Minus 3 is 0. Y equals negative 2 squared plus 2 times negative 2 minus 3. We've got 4 minus 4. Subtract another 3 is negative 3. Oh, and we're going below the x-axis now. And I'm going to keep going. So you'll notice that I stopped putting brackets around my values when I was squaring them once I got out of the negatives. That's completely optional. Do always continue to keep your brackets around these values when you plug them in because they are multiplying by another value, the coefficient. And if we drop those, then all of a sudden it'll start to look like 2 subtract 1 or 21, depending on the scenario. So keep your brackets when you're plugging in unless you are super confident that you will not make silly mistakes. And trust me, I still do to this day. So better safe than sorry. We now need to graph this. My maximum y value is 21. So I need to make 21 fit on this vertical positive axis. So 1, 2, 3, 4, 5, 6, 7. I go up by 7 squares. So I should be able to count up by 3 each time. So that's what I'm going to do. My scale is going to be 3 and negative 3. Now your vertical scale should match on both sides of the x-axis, just like horizontally they should also match. So I'm going to just go negative 1 and 1 for my x-axis because I only need to go up to 4 in those directions. So again, it doesn't matter where you start and which ones you do. I like just starting from the top because it makes sure that I don't miss anything or I'm less likely to. So we go 4 and positive 5 about here. Negative 3 and 0 will be about here. Sure that you're actually going through your points. Now, on the left-hand side, although I didn't plug in those values because these parabolas are symmetric, I can actually extend this further, and I can work backwards just visually to add in a couple more points and draw the full curve. Please note that this bottom here is actually a curve, not a V. So although it's called a vertex, it is not a V shape. So please do not draw a pointy little spot like that. Make sure it's curved all the way through. So we're not done yet. We're asked for a few more things. We're asked for x and y intercepts, the vertex, the equation of the axis of symmetry, the domain, and the range. So let's start. Our x-intercepts are where the graph crosses the x-axis. In this case, we've got two spots, number 1, number 2. So we've got x-intercepts, and we can just state the x values because the y equals 0 is implied. So it's going to be at -3 and 1. Our y-intercepts are going to be, we only have one, which is true to the function idea, where we only have one y value for every x, and it is here at -3. And again, I don't have to state my x coordinate because it's implied that it's 0 since it's on the y-axis. My vertex in this case is not 0, 0. It is my lowest point. So it's not a V shape at the vertex. So even though it's a V, it doesn't actually form a V. So it's this point right here. And if I'm not 100% sure what the coordinates are for that point, I'm going to check my table of values. It's -1 and -4. My equation for the axis of symmetry is that x coordinate of my vertex. It's this line. Every line needs an equation. A vertical line is always set to x equals, and in this case it's -1. My domain, my parabola keeps getting wider. It would go on forever. So my answer will be -infinity to +infinity. Do not write it in reverse. We are not going from positive to negative. We always start with the minimum. My range will be starting at the bottom of my parabola in this case. So starting at -4 and going all the way up to +infinity. So square bracket because it's an actual point, -4 and +infinity. But what if we cannot see the x-intercepts on the graph? Well, we're going to use our quadratic equation and use our strategy for factoring. So we'll start with 0 equals, because y is 0 when we're solving for our x-intercepts. And then we're going to factor. So in this case, we've got a simple trinomial. -3 is my product, +2 is my sum. So when I think about factor pairs, the only options are 1 and 3. Positive is what's remaining, so that's going to be my larger number. Subtract 1. So it's x minus 1, x plus 3. Both of these have the possibility of being set to 0, so I'm going to solve both. And you'll notice that these values actually match the ones that I came up with by looking at my graph. So it's great news. You can always check your answers. Make sure you drew your graph properly by solving your quadratic equation for the x-intercept. Not every equation is going to be factorable. We will learn how to deal with ones that aren't factorable, but we'll get to that later in our unit. So for now, if you come across one that is not factorable, don't sweat it. Don't worry. We will learn how to do that. While we're talking about them, the x-intercepts are known by a couple different names. The zeros of the function, or just the zeros, are Another name for your x-intercepts, because they are the values of x when the function is 0, when the whole thing ends up outputting a value of 0. They're also called the roots of the related quadratic equation. So you're going to hear these words kind of thrown around. The zeros of the function are specifically referring to the function as we solve it. The roots are when the equation is already set to equal 0. Now you're sitting there, okay, great, I can figure out my x-intercepts, or maybe you're like, I don't care if I can figure out my x-intercepts, but either way, you can do it. We can also actually identify our y-intercept. We do this by setting x to 0, so that's a typo here. Set x to 0 and solve, and then you can figure out your y-intercept as well. So for this particular question, we had graphed y equals x squared plus 2x minus 3. So instead of x, I'm going to plug in 0 squared plus 2 times 0 minus 3. This is 0, this is 0, y equals negative 3. And again, you'll notice that this is the same answer that I got by looking at my graph. And so those are the properties we're going to be working with for the rest of this unit and our systems of equations unit. So we've got to get really comfortable with them, get lots of practice in just identifying these different characteristics of quadratic functions.